Hi, everyone. Today we are going to learn about a little bit more about linear and angular velocity. I'm going to teach you about that. And just as a reminder, tomorrow you're taking that unit circle quiz and you're taking it on pair assessment. So you'll want to make sure that you bring your Chromebook fully charged. And then tonight's homework is a Math Excel on angular and linear velocity. Okay, so here we go. So the first thing we're going to do is we're going to talk about these two different situations here, where you have kind of like two gears, I guess, or two things. This makes me think of a bicycle all the time when I look at this. When you're looking at like maybe, let me get a better pen here. So if this is like the tire of your bike, and then this is like the little gear part of your bike over here on the left. And so they both have to spin. And when they both spin, it keeps the chain on your bike going around the two things. Okay, so it's going around and around. So when the chain is going around like this, the chain has to be going at the same speed because otherwise, as you know, the chain will fall off. So if this somehow is going at a different speed on one part, the chain would fall off. So that means if you're thinking of the green of the chain, if that is like the circumference of your circles, part of it anyways, so that would mean that these two linear velocities would be the same because think of, again, taking the chain, laying it out flat, that's the distance that you're moving around the two circles. So what this means, if this is like your radius of the smaller circle here, and here's the radius of the larger circle, the linear velocity of the smaller circle would be radius times angular velocity. And then the velocity of the bigger circle would be, again, your radius times your angular velocity. But I just said that since this is like the circumference, this chain or this green part represents the linear velocity of both of the circles, which means that both of the linear velocities have to be the same. So V1 would have to equal V2, which really means that you could just say, well, R1 times omega 1 would equal R2 times omega 2. Okay, so that's that scenario. The second scenario is like what we did in class for the trig whip activity when we were down in the atrium. So this would be like the first person here, okay? And this is the radius of the first person, the inner person. And then this here would be the second person. And so the radius of the second person I'll call R2. And if you remember from when we talked about this in class, or even when you did it down in the atrium, the person on the outside has to walk a lot faster to keep up with the person on the inside. The person on the inside is making the angle spin, so everybody's moving at the same angular speed. But the person on the outside has a much faster linear velocity because they're walking farther than the person on the inside. So for this setup, again, we can start off by thinking velocity 1 is R1 times omega 2, or omega 1, sorry, and velocity 2 is radius 2 times omega 2. But in this scenario, your angular velocities have to be the same, okay? So if I solve each of these for our angular velocities, what this means is if omega 1 or angular 1 is equal to angular 2, then you would do velocity 1 over radius 1 equals velocity 2 over radius 2. Okay, so a problem like this that has the circles inside each other called concentric circles, they have the same angular velocity. And then these two circles on the left that they're attached on the outside of the circles, they have the same linear velocities. All right, so let's try the first problem. That's, again, like gears, again, kind of like a bicycle. So remember, this one is where you have to set your linears equal to each other. Sorry, wrote that wrong. You're setting your linears equal to each other here, okay, like this. So I'm going to have R1 omega 1 is equal to r2 times omega 2. So r1 has a radius of 8 and has an angular velocity of 60 RPMs. And r2 has a radius of 12, and we don't know the angular velocity. That's what we're solving for. Now notice I'm leaving this in RPMs, and that is because I'm solving to get an answer in RPMs. So since I'm starting in RPMs and I'm ending in RPMs, I don't need to change this to radians. I can just leave it in revolutions. So 8 times 60 is 480, divided by 12 is 40. So 40 RPMs. And I hope that makes sense. This circle has to spin slower than this circle here, because the smaller circle has to go faster to keep everything up at the same speed as this one over here, the distance that it's moving. So this goes at a farther distance because it has this larger radius. Okay, question 2 here is that picture of two circles that are concentric. So we have a car that has let me get that over here. There we go. We have a car that has a radius for its wheel of diameter of 23. So that means the radius is 11.5. And it doesn't say anything about that speed for that car, that wheel. It gives you information about the speed for the larger wheel. Let me make this one just a little bit bigger. Okay, so what they're saying they did is the car normally has a wheel of 11.5 inches as its radius. But instead of putting that size wheel on the car, they're putting a wheel that has 25-inch diameter, so 12.5-inch radius. So when you do that, it's going to mess up what the speedometer says. It's not going to read it correctly. So we want to figure out what the speedometer would say if the car is actually moving at 55 miles per hour. And speedometers are in miles per hour as well. So we're going to start in miles per hour, end in miles per hour, so I don't have to do any dimensional analysis to switch this up. So this one, we're going to use the velocity over radius is equal to velocity over radius. So no matter what's happening, the car itself, when you hit the gas, the car is spinning the wheel at the speed it thinks it should be going based upon the spinning of the wheel. Okay, so it spins the wheel. You're saying, oh, I want to go 55 miles per hour, and it spins the wheel at that angular velocity to hit that speed. But it is set up for this radius, and so that's why it's going to be wrong. So we don't know the actual speed of the car that's going as a radius of 11.5. That's the one we don't know. We know that when the car is going 55 miles per hour, that is because we have a 12.5-inch radius wheel on the car. So we're going to solve this for the velocity that is connected to the smaller wheel. And hopefully you understand that since it's a smaller wheel, it should have a smaller velocity. So we're doing 11.5 times 55, and then we're going to divide by 12.5. So the speed of the car when it has an 11.5-inch wheel on it is 50.6 miles per hour, which means that's what your speedometer would say, which means if you think you're going 50.6 miles per hour but are actually going 55, it could cause you to be speeding and get in trouble, right? You could get caught. So this is why if you ever get new size tires on your car, you're supposed to get the car readjusted to match those tires. All right, moving on. So we're not obviously doing board work because I'm not here. So we're just going to do a few of the problems that we were going to do for board work, and then you can start your homework. So this says there's a cylinder with a radius of 3 feet that is spinning. We don't really care that it's a cylinder. It's just a circle. Okay. So we have some circle that is spinning or rotating at 100 RPM. So remember, that is your angular velocity. 100 revolutions per minute. Since I am trying to end in miles per hour, I'm going to have to turn this into radians. I'm also going to have to turn it into hours. So I'm going to turn this angular into radians. So I know I have 2 pi radians in 1 revolution. And I know I have 60 minutes in 1 hour. So the angular velocity changes to 100 times 2 pi times 60. Okay, so this now became 7. Actually, let me do this in terms of pi so that I don't have decimals, and I'll put the decimals at the end. So this is going to be 12,000 pi radians per hour. Okay, so my minutes cancel, my revolutions canceled, radians per hour. So that's the angular. To get the linear velocity, remember, you take the radius, which is 3 feet, and multiply by the angular velocity. This is radians per hour. All right, well, I don't want feet. I want miles. So now I have to get rid of the feet, and there are 5,280 feet in 1 hour. And I'm trying to get rid of the feet, so the feet are going to go in the denominator. So get rid of those, and I'm going to go ahead now and multiply the pi through, but this way I didn't have to worry about the decimal and like having it be wrong when I typed it in the second time. So 3 times 12,000 pi divided by 5,280 gives us 21.41 or 420 miles per hour. I would highly suggest you check these yourself with your calculator as well. So if you need to, pause and type it in and come back to make sure you're getting those correct. All right, number 2 is about a bicycle again. So we have a bicycle that has a 26-inch diameter tire, which means the radius is 13 inches. And it is traveling at 17 miles per hour. We want the angular velocity on a point on the edge of the rim in revolutions per minute. So we got a lot of changes we have to make here. So my linear velocity is 17 miles per hour. And that's going to equal my radius of 13 inches times my angular velocity. Okay. Well, I'm in inches and I'm in miles. So I'm going to first, I think, to make this easier, I'm going to change my inches into miles. It doesn't really matter. You could go to my miles into inches. I think I'm just going to do inches into miles. It's going to be a pretty small number, but that's okay. So I'm going to say there are 12 inches in 1 foot, and there are 5,280 feet in 1 mile. So this changes us into miles. So 13 divided by 12 times 5,280. And I'll write the decimal up here, but I'm just going to leave it in my calculator because it's really small. So 0.000189 is my decimal, and this is in miles. This is just miles, right? Okay. Times the angular. So now I need to solve for the angular. So I'm going to divide 17 by that angular. And this is going to give me radians per hour when I'm done, because when I solve for angular is always in radians. So when I divide or multiply to solve for this is going to give me a radian. So 17 divided by this number gives me 8,976, at least that's backwards, radians per hour. A lot of dimensional changes going on here. So that's our angular velocity. It's correct, but it's just not in the form we wanted, and we want it in revolutions per minute. So I need to get rid of the radians. So for every revolution, there are 2 pi radians, and I need to get rid of the hours. So for every hour, there are 60 minutes. Okay, and this is where we have to be careful. So you're going to take 89,760 and divide it by 2 pi times 60. And you're going to put parentheses around that so that you don't make a mistake and just do 2 pi times 60 and the calculator doesn't think you're dividing all of those values. So you should get for your angular velocity 238.096 revolutions per minute. And again, type this in yourself so you're practicing it. Otherwise, you might make a mistake in there. So I want to make sure I got all of that correct. I think that's right. Yeah, okay. Let's go and do one more and then we're going to be done. If you get something different than me, please let me know. On my other piece of paper, I have a different number. So check it out and let me know when you see me tomorrow if you got something different when you did all of this dimensional changes. All right, this is the last one we're going to do. I'm going to do with you anyways, and then you can start your homework. So we have a merry-go-round, and the merry-go-round rotates 3 times in 2 minutes. Okay, so they're giving you the angular velocity in rotations per minute. So 3 rotations or revolutions for 2 minutes, or 3 halves revolutions per minute, however you want to think of it, okay? Or 1.5 revolutions per minute, if that makes you happy. The kids sitting on the animals at the edge are 10 feet from the center, so that's your radius. How fast is the child spinning in feet per minute? So this one's at way less dimensional changes because everything is already in feet per minute. So this is a lot easier than the last problem. So your velocity will be 10 feet per 1 radian times 3 over 2. Well, there's one change I forgot to make, right? I got to change my revolutions. So I'm going to change my revolutions here. I'm going to do 2 pi radians per 1 revolution. And that's going to give us 3 pi radians per minute. You could have changed that, by the way, down here. That would have been fine, okay? So this is going to become 30 pi feet per minute. All right, so I'm going to stop there. And if you have questions, we'll try and make sure we get them answered tomorrow when you come back to class. Have a good day.